All right, welcome back. This is the second half of the notes for section P.1, the first section of our prerequisite chapter. We're going to start looking today at number sets, absolute value, and some more evaluating. A couple definitions, make sure you pause the video if you need some more time to write. We're going to first start out looking at number sets and the set notation. All right, so sets is just a collection of objects. Each object in a set is called an element. And then there's two types of things we can do with sets. We can do the intersection of sets and we can do the union of sets. If we look at the intersection of sets, it's written with kind of an upside down U symbol. It means you're listing all of the elements that are common to both sets. Make sure you highlight the word common. You're looking for things that both sets have in common. If we want the union of two sets, we use a capital U in between them. And it lists all of the elements that are in either set. So basically you just take everything that you see in either one and combine it. All right, so let's look at an example here. Set A contains the elements 8, 9, 10, 11, and 12. And this is considered roster method for designing a set where we have these braces and we just list each element that you see. Okay, set B contains the even numbers 2, 4, 6, 8, 10, 12, and 14. And set C contains the elements 1, 3, 5, and 7. So the first thing they're asking us to do is find the union of sets A and B. That means what do we have in sets A or in set B? We can put them all down. All right, so for our first one here, we would use this bracket or brace notation. We want to include everything that we see in set B and everything we see in set A. Typically, we put them in order. So we're going to start out. We need a 2, 4, 6. We've taken care of those three. There's an 8 that's common to both. We do not have to list it twice, just once. They both, this first set has a 9. That would be next. They both have a 10. Let's see. We've got 8 taken care of. We've got 9. We've got 10. Then we're looking at, we have an 11. They both have a 12. And we also need the 14. All right, so we've listed everything in sets A and B. We'll clean this up a little bit here so we can reuse them. All right, the second one asks us for the intersection of A and B. That means we need to find what is common, all right? What are those elements that they both contain? And when we looked through before, we said they both had an 8, they both have a 10, and they both have a 12. So we're going to list both or all three of those. All right, the third one asks for the intersection of A and C. So looking at this, set A starts with an 8, goes up to a 12. Set C has smaller numbers, 1, 3, 5, and 7. So if we're looking for what is common, there isn't anything. All right, so the symbol for that, we do a 0 with a slash through it. It stands for the empty or null set, meaning a set that has no elements. All right, there are a couple other set notations that we'll be learning as we go through this semester. Some very specific sets. We have sets of real numbers, which are any number that you can think of that's not imaginary. And within that, we have subsets of real numbers. All right, the first one, the numbers 1, 2, and 3. These are called the natural numbers. They're just our counting numbers. And we use an N, a capital N, for natural numbers. Okay. The only thing different in the next subset is that we add that 0 in. These are called whole numbers, and we use a W to represent the whole numbers. All right, so whole numbers are just all of the natural numbers with the added 0. trying to extend our page here. There we go. All right, so we're going to start down here, a little diagram. So our first thing we had was natural numbers. Okay, we've got that set of numbers. And now, if we add 0 into that, now we have the whole numbers. Okay. All right, going back up here, our third set or subset of real numbers. These are the integers. All right, integers are made up of positive and negative whole numbers. So now we're going to add all the negative versions to the set that we just had. Now, this one seems a little strange, but we use a capital Z to represent the integers. So if you want to think of it as zintegers, to help you remember that you want to use a Z for that. All right. So now we can go and add another set around that, the integers, and now we have those numbers. Sorry, I've already got 0 listed in there. We won't put that twice. All right, so we can add in all of the negative versions. The next subset. These are the rational numbers. Again, it seems maybe a little strange, but we are going to use a Q as the symbol for the rational numbers. Now we are looking for any number that can be written as a fraction, all right, or a ratio. So we added things like 2/3, 3/4, negative fractions. And if you think about it, all of the numbers that we already have down here, they can still be written as fractions. We could write 2 as 4/2. All right, so integers are going to go, rationals. Rational numbers are going to include everything we have plus all of those fractions, like 2/3, -1/2, things like that. Okay? The last subset is totally separate from what we've already been talking about. These are the irrational numbers, and we use a capital I for irrational. So it kind of splits this into a second grouping. So when you think about all of the real numbers, if we take all of this, we have the real numbers. We can divide that into sets of rational versus sets of irrational. And then within rational, we have all of these subsets, the integers, the whole numbers, the natural numbers. Rational numbers are things that cannot be written as a fraction. So things like the square root of 2. All right, that is an irrational number. If you try it on your calculator, it is a non-repeating decimal. Just keeps going. All right, pi is another common one. Even negative radicals, say negative square root of 8, would work. Now be careful, because say you have the square root of 9. That represents really the number 3, and that would be a rational number. So you want to make sure that the radical that you're talking about, like the square root of 2 or the square root of 8, is truly a number that cannot be written a different way. All right, so let's take a set of numbers. We have -7, -3/4, 0, 0.6 repeating, square root of 5, pi, 7.3, and the square root of 81. We want to see which of those elements fit into each of these subsets. So what did our n stand for? Those were the natural numbers. So our counting numbers. So which of the elements up there would be numbers that we could use to count objects? We can't count objects using negative numbers. We can't count objects using 0. We can't count objects using a repeating decimal or a radical like this. Really, the only number that would be a natural would be the square root of 81, because the square root of 81 really just represents a 9. Okay? Our next subset, the whole numbers. Whole numbers are all of the natural numbers with 0 added. So we're going to take the elements that we already had, square root of 81, and we're going to put 0 in with it. Now again, I would accept that. It's a little better if you put it in order. Just it's a little easier to look at the elements that are involved. But either one I would accept. All right, I. We often think of I as an integer, but remember we have integers. So this one down here are the integers. This one is asking for the irrational ones. All right, and then Q, remember, are the rational. All right, so let's go back down to letter E, the integers. That's the next build that we would have. We would take all of our whole numbers and now we're going to add all of the negative versions of whole numbers. So we can add in our -7 and then keep including the ones that we already had. Okay, rational builds on that. That's choice D here. We want to add in now all of the things that can be written as fractions. So going through our list, we still have -7. We can now add in -3/4. We had 0. 0.6 repeating. If you think about the value of that, 0.6 repeating is the same as 2/3. So we can include that, but instead of 2/3, I am going to write 0.6 repeating because that's the way it was written. But it does represent 2/3, just like that represented a 9. All right, square root of 5, that one would be irrational. Pi is irrational. 7.3 could be written as 73/10. So it can be written as a fraction or a ratio. So it would be rational. And then we also have the square root of 81 because that represents 9. All right, so our last one is the irrationals. Those are the ones that we could not include in the rationals. All right, so what are the elements up there that are not listed here as your rational numbers? All right, we only had 2. The first was the square root of 5. The second was pi. All right. Okay, another topic that is reviewed in this first section is our definition of absolute value. We often think of absolute value as a distance from 0 on a number line, but we do need to think of the algebraic way of stating that. Since distance can't be negative, absolute value is always a positive number or 0. So let's look at our first option. All right, this is saying that the absolute value of x is x, as long as x is 0 or a positive value. However, if we shift to a negative number, if x is negative, then the absolute value of x is going to be the opposite of our original x. And that seems a little strange, so let's look at an example. Okay, if x is positive, say 5, and we want the absolute value of it, we're just going to get 5. So this x stayed the same. But if x was -5 to start with, and we want its absolute value, those absolute value bars are going to change that -5 into its opposite to turn it into a +5. So that's where this little negative sign here comes in. It's actually an opposite symbol, but it is changing our value from a negative to a positive. All right, so our first example, the absolute value of 7 starts out positive, it's going to stay positive. Our second one, the absolute value of -4, it is negative, so we need to take its opposite, which makes it +4. All right, now the last two are expressions, and that might seem to throw you off a little bit. You need to look at what the overall value of it would be. Since pi is 3.14, we have 7 minus 3.14. That's going to end up being a positive value. So when we take the absolute value of 7 minus pi, we just get 7 minus pi. Okay. But in our fourth example here, the square root of 3 minus 4. If you look at your calculator, the square root of 3 is smaller than 4. So if you take the square root of 3 minus 4, you're going to get a negative number. And since negative numbers, when we take the absolute value, have to switch to the opposite, we are going to need the opposite of what we started with. And if we distribute that negative sign in, we end up with the negative square root of 3 plus 4, which also can be written as 4 minus the square root of 3 if we just turn it around a little bit. All right, either of these options would be an acceptable answer. All right, and then our last topic for today. We touched briefly on it in yesterday's notes, but looking at a little more extensive version of order of operations. All right, order of operations, we usually had the acronym PEMDAS for Please Excuse My Dear Aunt Sally. All right, the P here stands for parentheses. The E was exponents. My dear is multiplying and dividing. And Aunt Sally is adding and subtracting. So again, keep in mind the order that we have to do things in. All right, so looking at this first one, we have a very large fraction bar in there, which means we have to simplify everything in the numerator and everything in the denominator before we move on to actually doing that division. All right, so looking at the numerator, our absolute value bars are like a parenthesis. All right, so let's start by looking inside the absolute value bars. And inside we do have some exponents. So our first step is to deal with those exponents. All right, so 2 squared would be 4, 3 squared would be 9. Okay, inside that 4 plus 9 is 13, and the absolute value of 13 is 13. So now we have 12 divided by 3 times 5 times 13. Because that 5 is right next to the absolute value bars, it means multiplication. All right, on the bottom, if we look at that 6 squared, we can go ahead and do that exponent next. 6 squared would be 36. All right, and now going back, let's deal with any multiplying and dividing. Keep in mind we have to go left to right. So my first step is to take 12 divided by 3, which is going to give us a 4. Then we're multiplying times 5 and 13. All right, now I could do that multiplication. I'm going to leave it just for a second and simplify the denominator a little bit here. We have 7 plus 3, that's 10, and 10 minus 36 would be negative 26. All right, and now we could do some reducing here. We've got a 13 and a negative 26. We could divide those out and make it a 1/2. That is an option. If you don't have a calculator handy, that might be your best bet. Okay, without a calculator, I would go that route. If you want, go ahead and multiply. We have 4 times 5, that would be 20, and 20 times 13 would be 260. And then we are dividing that by the negative 26. Our final answer should be a negative 10. All right, and that type of equation or calculation should be done without a calculator at this level. All right. Again, if you find things that aren't in these notes that are showing up in your homework assignment, make sure you go back and look at the reading. For day 2 here, we're looking at page 17, 21 to 41 odds, 51 to 65 odds, and 111 to 119 odds. Thank you.